Electronic oscillators are meant for providing a stable and fixed frequency voltage waveform. Structurally, these are modified feedback amplifiers. When unity loop gain is implemented in a feedback amplifier, then it turns into an oscillator. The Barkhausen criteria, which is used in the design of oscillators, is actually an outcome of unity loop gain. As oscillator is a modified feedback amplifier, in its structure one can find an active element, an amplifier, and also a feedback network or beta network, which is usually passive. Different feedback networks are possible. Different basic active elements or amplifiers are possible. As a result of that, different types of oscillators exist. Electronic circuits, oscillators, first part, series on semiconductor devices and circuits, lecture number 10.10. All oscillators are single loop feedback amplifiers satisfying unity loop gain condition. Unity loop gain condition is usually called and known as Barkhausen criteria. When translated into mathematics, it is minus A beta equal to 1. This is an equation, a complex equation, as beta is a complex quantity. This complex equation implies two real equations, one for magnitude of loop gain, mod minus A beta equal to 1. Another on angle of loop gain, angle of minus A beta equal to 0, 2 pi, 4 pi, etc. For a feedback amplifier to become an oscillator, these two real equations, one on magnitude of loop gain, another on the angle of loop gain, these two requires to be satisfied by the circuit. In this session, the focus is mainly on understanding how unity loop gain feedback amplifier acts as an oscillator, how it is able to give output without any input. One can find answers in the present session, along with a discussion on one type of oscillators called RC phase shift oscillators. These are low frequency, audio frequency oscillators. They employ RC ladder network to act as beta circuit or feedback circuit in the structure of oscillator. As they employ RC circuit, these are called RC phase shift oscillators. Now let us move further to begin the course session. We begin the session with a definition to oscillator. It is an electronic circuit. Oscillator is an electronic circuit whose output is a stable, continuous sinusoidal waveform stable, continuous sinusoidal waveform, but with no input signal. So there is no input signal input to oscillators. It is an electronic circuit. What is electronic circuit? Electronic circuit is an electrical circuit in which there exists one or more electronic devices. Electronic devices are diodes and transistors. So oscillators are similar to amplifiers in that amplifiers are also electronic circuits. There is a dissimilarity between amplifiers and oscillators also. Dissimilarity is also there. What is that? Amplifiers require input signal to function, whereas oscillators accept no input signal. Here is shown the structure of oscillator. A basic amplifier is there, feedback is there, output is sampled, passed through feedback network, and then output of feedback network is multiplied by -1 so that the feedback is negative feedback, and then it is given as input to the basic amplifier. There is no other input to the amplifier, basic amplifier. Input to the amplifier is output of the feedback network multiplied by -1. That is input. Of course, for this configuration circuit to act as an oscillator, loop gain minus A beta should be arranged to be equal to 1. Some more points. Most of the oscillators are feedback amplifiers with the two special features. No input signal source. Here you can see there is no source. With the loop gain unity, as already mentioned, beta A minus beta A should be set to unity 1. Oscillators do not accept any input signal, whereas amplifiers require it. As there is no input signal, oscillators can be considered as amplifiers with infinite gain. So the connection, the relation between amplifiers and oscillators can be stated in one sentence as oscillators are amplifiers with infinite gain. Let us move further. As already shown, oscillators are modified feedback amplifiers. To understand the changes required to convert a feedback amplifier into oscillator, consider the output of a single loop negative feedback amplifier. Here is shown single loop negative feedback amplifier. The output of this amplifier can be expressed as X0 is Xs multiplied by A by 1 plus beta A. There are two factors. One is Xs, another is A by 1 plus beta A. These two factors multiplied gives output X0. Now let us designate A by 1 plus beta A by HF. With this designation, X0 becomes equal to Xs HF. With this expression, one can make certain observations. Output remains the same, X0 remains the same, and as it was when the input signal Xs is reduced by a factor and HF is increased by the same factor simultaneously. What he is trying to tell is, when Xs is made 2 times, it is increased 2 times previous value, and HF is decreased to half of its previous value, then X0 remains the same. If Xs is raised to 3 times its initial value and HF is reduced to 1/3 of its initial value, X0 remains the same. So output remains unchanged even when the input signal is reduced to 0 while increasing HF to infinity. So a logical conclusion of Xs increased to n times, HF decreased by n times do not change the output. A logical conclusion of this observation is output remains unchanged even when input signal is reduced to 0 while increasing HF to infinity. Input signal Xs reduced to 0 means removing the signal source from the amplifier circuit, and HF Rising to infinity means setting 1 plus beta A equal to 0 or setting minus beta A is equal to 1. Therefore, conclusion is, observation is, a single loop negative feedback system amplifier. It keep on giving same output x naught when we make two changes to the circuit. One change is removal of the input signal source. Another change is setting minus beta A equal to 1. This is exactly what is considered as structure of sinusoidal oscillator. The condition of unity loop gain minus A beta equal to 1 is called Barkhausen criteria. As loop gain is complex and function of frequency, the criteria implies two things, one on magnitude and the other on angle. A complex quantity has two things always associated with. One is magnitude, another is angle. So complex equation means two equations. One equation on magnitude, another equation on angle. In general, the transfer gain of the basic amplifier A is a real and fixed constant independent of frequency, whereas feedback factor beta is complex and function of frequency f. Thus, loop gain unity implies two things. Magnitude of loop gain 1, phase angle loop gain 0. It can be 2 pi also, it can be 4 pi also, it can be 6 pi also. Mathematically, one can state that mod minus A beta function of f equal to 1 angle minus A beta function of f equal to n 2 pi. N is 0, 1, 2, etc. In practical oscillators, n is selected 1 and loop gain is selected slightly larger than unity. These are the things that are implemented in a feedback circuit to convert it into oscillator. First equation is used to find frequency of operation, whereas second one is used to estimate minimum gain required from the basic amplifier. Barkhausen criteria, as already mentioned, it is unity loop gain condition the feedback amplifiers require to be satisfied. Technically, it is known as Barkhausen criteria. The frequency at which a sinusoidal oscillator will operate is the frequency for which a total shift introduced as the signal proceeds from input terminals through the amplifier and feedback network and back again to the input is precisely 0 or 2 pi. In practice, the value that is used is 2 pi. Oscillators will not be sustained if at the oscillator frequency the magnitude of the product of transfer gain of the amplifier and the magnitude of the feedback factor of the feedback network, it is less than unity. So it has to be 1 or more than 1. 1 is not practicable. Some more points regarding Barkhausen criteria. Stability criteria. If in an oscillator there exists one set of elements with a property that at the oscillation frequency these components introduce a large variation of phase with frequency, then d theta by d omega serves as a measure of independence of frequency of all other features of the circuit. The frequency stability improves as d theta by d omega increases. In the limit d theta by d omega becomes infinite, oscillator frequency depends only on the set of elements and becomes completely independent of all other features of the circuit. Barkhausen criteria and stability criteria. These two are important aspects pertaining to the functioning of oscillators. Now, several varieties of oscillators are there. when RC network is used as beta network or feedback network, those oscillators are called RC phase shift oscillators. If a FET is used as amplifier, then it is FET phase shift oscillator. If BJT is used, then it is BJT phase shift oscillators. If LC network, resonant network is used as feedback network, then the oscillator is called resonant circuit oscillator. If Wien bridge is used as beta network, then it is called Wien bridge oscillator. If a crystal is used as beta network, then it is called Wien bridge oscillator. Now, we are aware that all oscillators are feedback amplifiers. In feedback amplifiers, two different types of sampling is possible, two different types of mixing is possible. In FET phase shift oscillators, voltage series feedback is used. In BJT phase shift oscillators, voltage shunt feedback is used. In resonant oscillators, voltage series. In Wien bridge oscillator, voltage series feedback is used. First term voltage, it refers to sampling. Second term series or shunt refers to mixing at the input terminals. Here is given a table consisting of different types of oscillators and their important features. FET phase shift oscillator, BJT phase shift oscillator, Hartley oscillator, Colpitts oscillator, Wien bridge oscillator, crystal oscillator. In the next column, you can find expressions for frequencies. Next column, information is given regarding beta network or feedback network. In case of phase shift oscillators, as already mentioned, beta network is an RC ladder network. In case of Hartley and Colpitts, these two belong to resonant type of oscillators. LC circuit is used. In case of Wien bridge oscillator, Wien bridge is the beta network. In case of crystal oscillator, crystal is the beta. In the next column, magnitude of minus A beta more than 1. This is one of the conditions of Barkhausen criteria. How this condition gets translated in phase shift oscillator? It is in the form of mu more than 29. In BJT, it is in the form of HFE more than 44.5. Similarly, in case of Hartley oscillator, Colpitts oscillator, Wien bridge oscillator, crystal oscillator, how this loop gain slightly more than 1 magnitude, how it gets converted, translated into these structures. This information is provided. In the last column, significance or importance of various oscillators are given. Phase shift oscillators are audio frequency generators. Hartley Colpitts high frequency generators. Wien bridge oscillator is pure sine wave generator, whereas crystal oscillators are stable. They are well known for stability. Some points on phase shift oscillator. These are simplest kinds of oscillators with an amplifier connected in an inverting configuration, driving 3 cascaded high-pass RC circuits. It is operated in class A in order to keep distortion to a minimum. Chiefly suited to audio frequencies from several Hz to several 100 kHz. Lower limit of the frequency is set by practical values of components, whereas upper limit is dictated by slew rate and frequency response limitations of op-amp or active element used in the circuit. FET or BJT is used as basic amplifier. RC phase shift network is used as feedback network. Tuning is done by changing any of the impedance elements in the phase shift network. However, for large range variations, the 3 capacitors are varied simultaneously. Such variations are preferred because they give constant input impedance to the phase shifting network and constant magnitude of beta and A beta. Ultimately, it results in invariation of amplitude of oscillation and the frequency is adjusted. This is the basic structure. This is amplifier. R, three resistors are there. C, three capacitors are there. This is ladder network. Here you can see basic structure of phase shift oscillators. In this slide in A is shown FET phase shift oscillator. Small signal equivalent circuit is shown in B. Here one point requires to be mentioned, understood. What is that? In practice, we implement angle minus beta A is equal to 2 pi. Just that. 1 pi is provided by feedback network. 180 degrees shift is provided by feedback network. Another pi 180 degrees is provided by the active element. Here is shown FET amplifier in CS. We know pretty well CS amplifiers exhibit 180 degrees phase shift between output and input. So this fellow provides 180 degrees. Remaining 180 degrees pi is provided by the ladder network, RC network. Equivalent circuit is shown in B. The transfer function of RC phase shift network is minus beta is equal to Vf prime by V naught. It is equal to, using circuit analysis techniques, one can show it as 1 over 1 minus 5 alpha square minus j 6 alpha minus alpha cube. Here alpha is 1 by omega RC. The frequency of operation of this oscillator, it can be found as 1 over 1 by 2 pi RC root 6. At this frequency of oscillation, beta is 1 by 29. But beta A, it should be slightly more than 1. So when beta is 1 by 29, A, gain of the basic amplifier should be more than 29. So FET with the amplification factor of less than 29 cannot be made to oscillate. We have to select a FET whose amplification factor is more than 29. Here is shown BJT phase shift oscillator. This is BJT. Again you can see here also, here C, R, C, R, C, R. Of course R3 is appearing in the diagram, but R3 plus Ri, input resistance of the BJT, Ri, together is R. R3 plus Ri is R. In principle, this is same as FET phase shift oscillator. Only difference is there it is FET, here it is BJT. Of course, the feedback configuration here is voltage shunt. There is, it is voltage series. The loop gain for the circuit is minus beta A is equal to I3 by IP. Total phase shift to be 0 leads to an expression for frequency of operation as 1 by 2 pi RC multiplied by square root of 6 plus 4K. Here K is RC by R. RC is collector resistance and R is ladder circuit resistance. Loop gain magnitude more than unity for oscillations to start. It leads to HFE more than 4K plus 23 plus 29 by K. So a transistor with HFE. HFE is current gain. Short circuit current gain less than 44.5 cannot be used in this phase shift oscillator. With this we come to an end of this session. To conclude, to close down, we recollect the important aspects that are discussed in this session. Unity loop gain condition or Barkhausen criteria has been introduced, and it is also explained how implementation of this condition leads to the transformation of feedback amplifier into an oscillator. And then one type of oscillators, RC phase shift oscillators, are introduced along with their tuning mechanisms, frequency of operation, and other important features. Hope this session is useful to you. We meet again in another session with a new topic soon.